Hello everyone, welcome back to Learn by Doing channel. In today's session, we are going to explore two different ways to train and visualize the neural network, both on the training side and also in the final results. We are going to use NumPy, Matplotlib, and sklearn. Different packages will be deployed, and we are going to see how in details we can manipulate these projects. The first version, we're going to introduce the interactive widgets to allow you to manipulate the different parameters and see the neural network training process dynamically. The second version, we are going to print out many different versions of the neural network training process to let you understand and get intuitive impression of this machine learning structure. By the end of this walkthrough, you will understand how weights are updated, how to visualize the learning process, and you will also be able to try it by yourself to test and to manipulate the code to better learn artificial neural network. Before we start, don't forget to subscribe for more hands-on tutorials. Now, let's go to the code. First of all, we choose the Iris dataset. Before we jump into the code in detail, let's briefly introduce the Iris dataset. It is a classic dataset that's widely used for machine learning demonstrations. The dataset contains 150 samples, each representing a type of iris flower. It includes 4 different features for you to identify the type of the flower, and these features help classify the flowers into 3 different species: Certosa, versicolor, and virginica. The goal of this tutorial is to train a neural network to classify each sample based on the input features. This makes the Iris dataset an excellent starting point for beginners in machine learning and neural network. Now let's take a look at the first version of the code is interactive neural networks with widgets. In this first version, we've incorporated interactive widgets that allow you to customize the neural network's architecture and the learning process on the fly. You can modify the number of layers, neurons per layer, activation function, and learning rate without touching the code directly. So as you can see here, after running this code, you have this navigation pane where you can change the different parameters layout of the neural network, so you can try to see how different type of the neural network can be trained and get different results. In this code, first of all, we need to prepare the different dependencies. Now we start the first step, loading the Iris dataset. We start by loading the Iris dataset. The dataset is small but excellent for demonstrating neural networks. It contains 150 samples, each with 4 input features and 3 target classes. Then we prepare the input features X, target label Y for the training. Step number 2, we pre-process the data to prepare them ready for training. We use one-hot encoding to convert categorical labels into binary vectors, which is necessary for multi-class classification in a neural network. Then we train test split the dataset, which means that we split the data into training and test datasets. 80% of the data is used for training, 20% of the data is used for testing. Then we also normalize the features. Normalizing the feature will speed up the convergence of the neural network by ensuring that all the features have similar scale. Step 3. Now we are introducing the widgets for dynamic interaction. First of all, we need to add the widgets that allow you to customize the neural network structure and the parameters dynamically. You can adjust the number of layers, neurons per layer, activation function, and the learning rate, all without modifying the code manually. So in this way, we can have a very dynamic display, as you can see after running this code. And here we can set the number of layers using the slider, specify the number of neurons in each layer by entering the values separated by commas, like this example here. The first layer is 4 neurons, second layer 5 neurons, third layer 3 neurons. Then we can have different activation functions. As you can see here, we have sigmoid, tan, relu. These widgets give you full control over the network structure and the training parameters without modifying the code. In the end, we need layout of the widgets to actually make sure all the widgets we set above will be shown correctly. Part number 4, as you can see here, we need to define the different activation function and their relevant derivative format. In this way, we are going to use these functions in the training process. Then, step number 5, we are building the build and train model function. In this function, we are going to initialize the weights and biases and also keep tracking the track the weight, W1, W2, loss, and accuracies. In this way, we are going to keep all these calculation results in the process and shown eventually. Then, after choosing the activation function, we are going to move to two most important parts of the neural network training. Forward propagation is going to get our input feature and reach to the final output of the neural network. Backpropagation is going to do the reverse and use gradient descent and chain rule to adjust the weights and the biases to reduce the error. Then during the training process, of course, as a result, we need to update the parameters accordingly, and we also need to compute the loss value. Then there will be the training loop with the progress bar. The reason I'm adding the progress bar is to understand where we are during this training process, especially when you train the neural network with large data sets. This is quite important because you can understand where you are. Then in this loop, we are actually implementing the whole training process from forward propagation to backward propagation, and then update parameters, then check the weights and losses for our later data visualization and comparison. Then we also compute our accuracy and print out each epoch how is the loss and the accuracy value. Then we also have the softmax function for the output layer. Part number 6, visualization function to plot loss and then we also have the function to plot loss and accuracy. In addition, we have the 3D gradient descent plot to visualize the gradient descent process where we are tracking the loss value as we update the weight W1 and W2. The code seems a little bit long, but the main purpose is that we want to anchor our visual to some parameters and see how the loss value could change after each training step. And we also added several parameters to make sure that we can view the 3D graph from different angles. Of course, you can also update this part to use Plotly or other packages to get more dynamic visual. But for me, I just use this simple version. They are static, but the general workflow is smooth and fast. Then we also have the VBox to accumulate the results of multiple runs. Part number 7, also the final part, is to design this run button for us to initiate the whole process and also to display the interface. So in this part, we make sure that whenever we finish setting the different parameters and we click run artificial neural network, and we are going to see the different neural network being trained and showing us the results, as you can see here. Now, let's quickly review some of the results we did before. For example, the first one, we have a 3-layer neural network with 4, 5, 3 counts of neurons in each layer. We use sigmoid as activation function inside the neural network, and we have a learning rate of 1%. And you can see this is the training process with the decreasing loss value and increasing accuracy value, and this is a plot about loss and accuracy after each epoch. And also we can see the 3D display of the learning process. This display is not comprehensive, means that it cannot include all the scenarios. For example, we are now only picking 2 weights value from the whole training process. As you know, we have many weights and we have many neurons in the neural network. It is not so easy to see the display of all the parameters alongside with the loss value. But here we pick these 2 weights just to let you know that this is a dynamic process, and you can also adjust the values you want to display in the 3D graph. For example, you can choose other values other than the weights I picked here. As you can see, the loss value reached to the lowest point from the highest point. As you can see, the first one on the left, The starting point, we have weight 1 as 0.46, weight 2 0.11, and loss value 1.9. And it will go to the middle point, the green dot. We see the weights are updated and the loss value becomes 0.77. Then we come to the end, we have two weights, W1, W2, and also the lowest loss. So in this way, you can have an idea that this process is dynamic. But remember, the loss value is actually attached to a multi-dimensional parameter involvement. So you can try to visualize it with some of the parameters, but to visualize all the parameters changing together with the loss is quite challenging. And we as human, I think the 3D display is our limit about the visual side. That being said, as you can see, we can change the different parameters and see different neural network can be trained and how the loss value can evolve. Me personally, I prefer such kind of visual for me to learn better how the model are trained, how the values are changed and updated, and also help me improve the understanding. Now let's take a look at the version 2 of the code. So basically the process does not change much, but only in this version, I do not rely on clicking the run button to run the neural network. I actually use the code to generate the grid of the different training process directly with different setting of the neural network structure and the activation function and so on. As you can see below, after running the code, I'm going to see this grid of the graph. So now, as you can see, you have a visual comparison of different artificial neural network structures. So with this kind of comparison, you can either choose the model that you prefer with different metrics comparison, or you can even dive deeper. For example, you want to understand why the different activation function could make the neural network behave differently. You can also get some insights from such kind of comparison. As you see, the first block is about the sigmoid activation function. The second one is about the tab activation function. The last one, of course, is about the ReLU activation function. You see different activation function, different neural network structure. We have the different involvement or different trend of the loss, accuracy, and also the involvement of the gradient descent procedure. So I do encourage you to compare these different models both from a very strict sense, like the loss value, accuracy value, and different metrics, and also from the visual side. You can also compare them to, first of all, to learn about the different neural networks, and also to make better decisions to best utilize this model to your use case. So basically today we have gone through two versions of the code to train the neural network and visualize the neural network. Of course, we could have a more detailed display and we could add additional metrics to see the comparison of the models. But at this moment, I wish you could get some insights. If you prefer the visual comparison, this is an example that you can incorporate into your analysis, your research. I really wish that this video could be good inspiration for you. If you like my video, please subscribe, leave a comment, and share. And please stay tuned for Learn by Doing channel. See you next time. Bye bye.